Collaborative system of autonomous drone and vehicle has been one of the interesting topics in the field. Collaborative system of unmanned machines can be used to create social value. These unmanned machines have greater accessibility than humans in various situations such as disasters. Also, it can be used in everyday situations such as delivery service. D2V team had been working on this project since summer of 2020. This semester, we upgraded our machines. Now, our drones have higher load capacity, and our vehicles now operate with greater number and various platforms. To fully utilize these resources, we decided to optimize each system first, before integrating into a whole system. From now on, we'd like to explain our work behind the system. We built a system that requires adjustment only in Mission Planner to perform whatever given mission, which means that perception and control unit operate independently. This not only reduces complexity in designing new mission, but also the system to become more versatile. For localization of the drone, 3 separate navigation systems are integrated. In certain environments, such as in the middle of high-rise area, satellite signals are easily interfered. This can be resolved by utilizing RTK GNSS, which receives signal from base station that contain required data for calibration. Orientation is measured by ARs, and the position data from GNSS is fused together. Finally, this data passed through extended Kalman filter to estimate the pose. In order to further compensate inertial and satellite navigation, vision-based navigation system is used. Visual odometry method can detect changes in camera's pose from series of images. SPO method is used to take advantage of 2 methods, picture-based method and direct method. SPO method require low computation costs which allow real-time video processing up to 400 frames per second. LiDAR is used to provide scale information to VO and to create 3D map of the surrounding environment. Point cloud data generated by LiDAR allow understanding of the surrounding terrain. Using this point cloud data, 3D spatial map based on voxel is made to detect obstacles. Now, the drone's pose information and the map around, created in precision unit, are utilized in planning unit. The following figure is a simple configuration diagram of the drone's autonomous flight system. The planning unit calculates the required path in the current state with the finished state machine. Then, the control unit controls the drone to follow the path received from planning unit. For optimal trajectory generation, we set up minimal energy problem by expressing the drone's dynamic model as a state-space equation. Using the state-space equation as constraint, an optimization problem is defined, where the control input value, u, is minimized. In simulation, 4 arbitrary waypoints are set in a 3D space, and the trajectory shown in the figure is the solution of the optimization problem. In case of obstacle avoidance, in every keyframe, the shortest path of the map is calculated using the jump point search algorithm, and the waypoints B1, B2 are extracted from the path. Finally, calculation of minimal energy trajectory passing through B1, B2, and the local goal point is made. To reduce tracking error correction is introduced. Based on the dynamic model, the error of the next time step is predicted. Then, calculate additional control input to correct the tracking error.
The system and architecture of the vehicles are also a significant part of our project. Similar to drones, tasks are no longer influential in how the control and perception unit operates. The 3-layer planner structure of mission, behavior, motion planner decides the details of operation. Today, we're not going to talk about the components of autonomous vehicles because we've already presented the details throughout the past semesters. Instead, we will focus on the adaptive cruise control and global path planning implemented this semester. In implementing adaptive cruise control, our mission was to follow the vehicle located in front of our car at a constant distance. In order to accomplish our mission, we've detected the vehicle and calculated the distance and speed of it. We wanted our car to maintain a constant distance from the vehicle in front of ours. Therefore, we implemented Deep Learning Model YOLO version 3 to detect the license plates of the specific vehicle. Open dataset from AI Hub was used to train the model. The average precision turned out to be 0.96, confirms that our own trained model works well. If there is no vehicle detected in front of our car, it will maintain its speed constantly. And when the car detects a vehicle ahead, it will change the speed to retain the safety distance from the other vehicle in front of ours. The control system is explained in this figure. We decided to use PID control to get the optimal velocity of our car. Therefore, we tuned PID gain values using the Ziegler-Nichols method. Furthermore, we chose to lower the K gain compared to the standard Ziegler-Nichols method. This way, it is expected to prevent errors in detecting other vehicles and any possible collisions. Next, in the global path planning, we implemented 3 processes. First, in the perception process, we conducted a study on recognizing objects and their sizes. And we got vehicle location and heading information with GPS and IMU sensor. In the planning process, with this GPS and IMU sensor information, we set the path and determine actions based on vision information. Lastly, in the control process, the main task was to find the steering angle and speed to follow a given path. An operation is calculated based on coordinate information of 2 points. Through these 3 processes, we implemented the vehicle to turn left toward the target point. We continued to increase the research depth of the platform. Based on what we've developed this semester, we have planned to conduct an integrated research on the actual vehicle I-30 and the drone. This is the end of our presentation. Thank you for your attention.